On Peru's Pacific coast, green fields appear where almost no rain falls. Blueberries leave them in refrigerated containers bound for supermarkets. In 2025, Peru's agrarian exports reached $15.013 billion. But the desert did not create that value. A machine did. Water is captured from Andean rivers, pushed through tunnels and canals, divided across farms, measured through drip lines, inspected, chilled, sealed, and moved to port. If one intake, sensor, certificate, or transport link fails, the entire export sale can be jeopardized. This is how public engineering, private capital, and trade rules turned scarce water into economic power. And what happens when that system reaches the resource it cannot manufacture? Consider Chavimochic in La Libertad. The system diverts water from the Santa River toward Chao, Viru, Moche, and Chicama. Its first two stages are not merely canals beside crops. Official project records describe a diversion intake, a main canal, a cross-basin tunnel, the Viru siphon, drainage works, hydropower, and a water treatment plant serving Trujillo. Together, those components change what the coast can support. They regulate and move a resource that local rainfall cannot reliably provide, then distribute it across production zones and an urban system. That hydraulic platform took decades. Chavimochic's first two stages were executed as public works between 1986 and 2012, with reported investment of $960 million. An export farm can look private while resting on public geography built decades earlier. Regional public works regulate and route river water at a scale no individual farm could reproduce. Once delivery becomes credible, private operators can make a different class of commitment: preparing land, installing precision irrigation, organizing harvests, and building the packing and working capital systems required for time-sensitive exports. Almost makes the geographic transformation even more literal. It carries Huancabamba river water through a 20-kilometer trans-Andean tunnel toward Lambayeque. Its first phase design covers 43,500 hectares, although that design area must not be confused with proof that every hectare is currently planted. An early regional report 4 months after irrigation began said more than 1,000 hectares had been planted. That dated figure shows ramp-up, not today's acreage. The mechanism is durable. Engineering crosses the continental divide, and water access makes intensive investment possible on arid land. At the farm boundary, bulk water enters another system. Pumps pressurize it. Filters protect drip lines. Fertilizer can move with each scheduled dose. The objective is not merely to use less water, but to make timing predictable for crops whose size, quality, and harvest window determine their export value. That is the hidden conversion. The canal does not grow blueberries. It makes the blueberry business financeable. Water alone does not produce an export empire. It creates an option. Private capital must convert that option into crops with uniform quality, traceability, and carefully timed harvests. Then public institutions must make those crops legally admissible abroad. This is why the Peru-United States Trade Promotion Agreement, in force since February 2009, and the Peru-China Free Trade Agreement, in force since March 2010, belong in the same story as dams and tunnels. Border access and customs rules shape where a harvest can be sold. Phytosanitary access determines whether it can enter a specific market at all. SENASA, Peru's agricultural health authority, maintains crop and destination-specific export protocols that can govern the product from the field through the finished shipment. These rules are invisible infrastructure. A fruit is not export-ready merely because it has been picked. The production site, pest controls, inspections, treatment, documentation, and final seal may all have to satisfy an agreed protocol. SENASA reported that in 2025, Peru exported 540 agricultural products to 115 destinations, totaling more than 3 million tons. Those are the agency's reported national figures, but they reveal the scale of the market access machinery behind the farm gate. For blueberries shipped from Lambayeque, a documented SENASA cold treatment procedure shows how exact that machinery becomes. The fruit is pre-cooled. 3 sensors measure pulp temperature. Low temperature is maintained continuously. Containers are sealed, records preserve traceability, and phytosanitary certification accompanies the load. Refrigeration is only one part of the process. The cold chain is also measurement, custody, proof, and permission. A temperature failure or broken traceability record can make a shipment non-compliant and jeopardize its sale, even if the fruit itself was grown successfully. The port is the final conversion layer. In December 2024, SENASA certified 4,000 pallets of table grapes for export from Paracas to the United States in refrigerated shipholds, a load it described as equivalent to almost 200 containers. That operation does not prove that port logistics alone caused the 2025 export record. It demonstrates something narrower and more useful. The crop's value survives only if inspections, cold conditions, loading, and ocean transport operate as one sequence. The farm produces fruit. The system produces an internationally accepted shipment. Now the headline can be read correctly. Of Peru's $15.013 billion in agrarian exports, $1.912 billion came from traditional products and $13.101 billion from non-traditional exports. That does not mean desert farms produce the whole total. Coffee, cacao, and other crops grown outside the engineered coast are included too. The desert system is a major engine inside a larger national machine, not the entire machine. Fruit and vegetable exports reached $8.104 billion in 2025, equal to 61.9% of Madagri's non-traditional agrarian category. Within the wider total, fresh blueberries generated $2.457 billion, grapes $1.960 billion, and avocados $1.363 billion. Together, those 3 crops generated $5.78 billion, more than 1/3 of the national total. These values help explain why operators may commit capital to precision, speed, and cold logistics. They also show why water reliability becomes economically powerful. When high-value output depends on a controlled growing window and an uninterrupted route to market, access to water is not merely an agricultural input. It can influence land value, bargaining power, and the confidence to invest. The gains do not imply equal access. The OECD describes Peru as a dual agricultural economy, a technologically advanced export-oriented coastal sector alongside a very large small farm sector. Nationally, it reports that 79% of farms are smaller than 5 hectares, while 0.2% of large farms account for more than half of agricultural land. That statistic does not prove that every irrigation project has the same ownership pattern. It does warn against imagining that every farmer enters a newly watered landscape with the same capital, legal capacity, packing facilities, or negotiating power. In ICA, peer-reviewed research argues that agribusiness elites consolidated influence over state and non-state actors, while scarce groundwater was overexploited under fragmented governance. That reported scholarly finding is structural, not an accusation against unnamed companies. When production depends on permits, wells, canals, export protocols, and costly logistics, power can accumulate around actors able to coordinate the whole chain. The integration making exports reliable may disadvantage producers who control only a field. Water stress turns that political question into a physical constraint. Peru's water authority found in 2011 that extraction exceeded recharge in the Ica, Villacuri, and Lanchas aquifers and maintained restrictions on new wells or increased extraction. In April 2025, it modified the restriction regime, By June 2026, the authority was using precision drones in Via Curi to detect unauthorized wells and prevent over-exploitation. This is not a distant hypothetical. The boom already operates inside rules created because groundwater demand exceeded what the aquifers could safely replace. The national context adds pressure without predicting the fate of any single basin. The OECD reports that agriculture accounts for 85% of Peru's freshwater withdrawals and identifies extremely high water stress along the coast. Peru also lost 56% of its glacier surface over roughly 6 decades, according to the National Glacier Inventory. That loss should not be converted into a precise claim about supply to every coastal project. Basin hydrology differs. It does show that the mountain water system is changing, while coastal production remains dependent on controlled delivery. Peru's proposed answer is more infrastructure, but the status labels matter. Midagri has described a strategic portfolio of 25 large irrigation projects with estimated investment of $24.061 billion and intended expansion of more than 1 million hectares. That is an announced portfolio estimate, not money already spent, financing already secured, or acreage already operating. The gap between a portfolio map and a flowing canal is where procurement, contracts, engineering, hydrology, and political authority must align. Shavimoshik 3 shows that gap. In February 2026, the Water Authority reserved 933.59 million cubic meters per year from the Santa River for project demand covering 72,795 hectares. A legal reservation is not delivered water. It does not prove that the dam, siphon, and distribution works are complete. In March 2026, the project authority said physical work on the Rafael Quevedo Dam and a third Viru siphon line was projected to begin in August, subject to funding and procurement steps. By August 10th, there was still no official confirmation that construction had begun. The project remained a proposed restart, not an operating expansion. Majes Siguas 2 shows a different execution risk. Its concession was signed in 2010, accumulated 13 amendments, and entered arbitration over termination while the project title was being transferred to Midagri. In March 2025, Pro Inversión and Midagri signed an assistance agreement to evaluate and structure alternatives for resuming the project as a public-private partnership. That is restructuring, not operation. The infrastructure may still advance, but its timing, financing, allocation rules, and eventual benefits remain contingent. Several futures could follow. None is a prediction. If financed, procured, built, and reliably supplied, unfinished projects could expand irrigable capacity and seasonal exports. If groundwater enforcement tightens or surface water reliability worsens, farms may face higher costs for pumping, transfer, storage, or changing crops. If new rights favor actors already financing the export chain, expansion could deepen concentration. Different allocation and access rules could produce a broader distribution of opportunity. That is Peru's contradiction. Efficiency can make each unit of water more productive, yet total demand can still rise when planted area and crop intensity expand. Export revenue can validate another canal, increasing dependence on institutions that allocate scarce water and finish complex projects. Its linked layers create resilience and vulnerability. A stalled dam, depleted aquifer, failed cold treatment, or closed market does not remain local. It travels through the chain. Return to the green field on the Pacific Desert. At first, it looked like nature had been defeated by a farming miracle. Now, its straight rows carry a different meaning. They are the visible signature of a carefully negotiated system. Andean water moved by public engineering. Land activated by private capital. Fruit admitted by sanitary rules. Value preserved by refrigeration. And access extended through ports and trade agreements. The field is real. So is the export success. But neither is self-sustaining. What grows there is not simply a crop, it is an engineered contract, and its future depends on whether Peru can keep every part of that contract flowing.